we're going to do electric field potential and energy. It is very similar to gravitational field potential and energy. All the equations and the formula are going to be almost identical, but instead of mass, which is the gravitational field potential, we have charge instead. Another thing is that a mass is always attracted to another mass. The potential energy and the potential is always going to be negative. Here, however, we're talking about a small positive test charge near another positive charge, and that's going to be a repulsive force. So here the potential energy and the potential are going to be positive. It's at zero, which is at infinity, the potential is zero, and as you bring it closer to the charge it increases. But look at that next. So we have the same as before. Basically, it's like gravity. The potential energy is compared to the point which is at infinity. It's a standard for all charges. We have what's called the electric potential, which is basically the electric potential energy per unit charge. So, the definition: the electric potential, is the work done per unit charge in bringing a small positive test charge from infinity to point P. So at infinity it is zero, at P it will have a positive value. Remember that the potential energy is the work done, which is the force times distance. So we have to look at this. This is the potential energy. It's the force times by distance, which is kqq over r, not r squared, because we're multiplying by the force by distance. The potential energy per unit charge is this divided by a small charge. So divided by Q, and we end up with what's called the potential, the electric potential. We write V for this. And it's going to be KQ divided by R. So there we have it. This is the unit. This is the potential, and it's KQ over R. And the unit of potential, it can be the joules per coulomb, but it can also be volts, and we're going to get onto that later. State and apply the expression for electric potential due to a point charge. So this is the expression. V, the potential, is KQ over R, the potential energy per unit charge. Now, what is the unit going to be? Now, we know that potential is the potential energy per unit charge. So it's going to be the joules per coulomb. So joules per coulomb. But we also know that this is going to be equal to volts, because in the electricity topic we know that the amount of energy per unit charge is also equal to the voltage at that point. So this is also given to the unit volts. State and apply the formula relating electric field strength to electric potential gradient. This is a point that many students have difficulties with. So we look at the electric field. Electric field is the field strength is E is equal to KQ over R squared, which is the force per unit charge. The electric potential that we've just looked at is V is equal to KQ divided by R. Of course, this is the same Q. This is a large Q, the large charge which is causing the electric field. Now, the rate at which the potential changes over distance is the change of V divided by change in R, change in distance. So this is V, so we divide it by a change in distance, and we're going to get something like this. Change in V divided by change in distance is equal to KQ over R squared, because we've divided by the distance here. This is a weak proof. You need, if you had calculus, differential calculus, this would be a very standard proof to do, but I'm skipping over the details here. But just understand that the rate at which the potential changes with distance is equal to KQ over R squared. Now this looks familiar. KQ over R squared is also equal to the electric field strength. So So the potential gradient, which is the rate at which the potential changes with distance, is also equal to the electric field strength, in the same way that the potential gradient, the gravitational gradient, is equal to the gravitational field strength in the last topic. So this is E is equal to the potential gradient. And the potential gradient basically tells you how the potential changes with distance. And the units are going to be volts per meter, or newtons per coulomb, because remember, it's the same as the electric field strength, the amount of force per unit charge, newtons per coulomb. So this delta V over R is equal to KQ over R squared, which is the same as this, and therefore we have E is equal to delta V over delta R. So sometimes we can express the electric field as this way. Sometimes we can express it as a potential gradient. If we know how the gradient changes, the potential changes with distance, that gives us a value for the electric field. And of equipotential surfaces due to 1 and 2 point charges. Now, the pink lines here are the electric field lines going from positive to negative, this way. Okay, the equipotential lines will always be at 90 degrees to the field lines. You notice this line here, and so on. So this is when you have a positive and negative charges. This is what the field pattern will look like, and this is what the lines of equipotential will look like. And here we have some more examples. This is pretty much the same thing here, with the lines, the field lines in blue going from right to left. The lines of equipotential are going to always be at 90 degrees here. Here we have two similar charges. You see the field lines are going to be repelling each other, but nevertheless this must always follow the contours of the equipotential, must always be at right angles to the field lines. Here's another example. This is a negative plate with a positive point charge. The field lines will go from positive to negative, but the equipotentials will always be at 90 degrees to the lines of force. And here we have another thing here. Now this is positive. The interesting thing here is that because it's we have a point here, the electric field strength here is very strong. The lines of equipotential are very close together. So there's a very strong electric field at the point of a needle, for example, if it's charged. And this is a good, what I like about this one, the one on the top left corner here, is that we have a positive charge. Here we know that near the charge the field strength is very strong because the lines of force are very close together. Also, the lines of equipotential are also very close together. As the field gets weaker, as it goes away, the lines of equipotential get further and further apart. Another point is that since we're talking about an electric field, we know that at infinity the potential energy, or the potential, is zero, and as you approach the charge, then the potential increases. So this line of equipotential is the 30 volt line. Then we have the 50 volt line, then the 70 volt line, and the voltages get higher and higher as you approach it. The potential gets greater and greater. This is an interesting one. This is the same as before, the same as this one here, but it's paired with a negative charge. Now, halfway between them, this is always going to be positive. This is always going to be negative, because remember, this is going to be an attractive force. The point in the middle is always going to be 0, provided these are the same charges. So this is 0 volts in the middle here. Notice that this is a 0, and as it approaches the positive charge, it becomes greater. As it approaches the negative charge, it becomes more and more negative, minus 30, minus 50, and minus 70, and so on. Here we have two similar positive charges, and you can see the lines of equipotential moving around like this. This is a question that you'll be asked on the quiz. We have two plates. This is at a potential as 60 volts. This is a potential of 20 volts. There is a distance of 10 centimeters between them. So we can draw these lines of equipotential between 60 volts and 20 volts. We know that between two plates the field strength is going to be constant. The lines of pull are going to be parallel and equidistant. It also means that the equipotentials are going to be parallel, equidistant, always at 90 degrees to the field lines. So if this goes from 60 to 20, we go 60, 50, 40, 30, 20. So that's going to be fairly clear. Now the question is, what is the field strength going to be in here? Now we know that the field strength is equal to the potential gradient, the rate at which the voltage changes with distance. So what is the change of voltage? We go from 60 to 20, 60 minus 20, divided by this distance, which is 0.1 meters. So it's going to be 0.1. So you're going to find the answer, which will give the electric field strength here, and it can be in two units. It can either be volts per meter, or it can be newtons per coulomb. This is a question we may get to do in class. We have these are the lines of equipotential between X here and Y, and we have to sketch what these look like. How does the electric field look like going from X to Y? Well, you can see here that the lines are the similar distance apart. So that suggests that the electric field is going to be constant. About halfway, however, as we approach Y, we find that the lines of equipotential get further and further apart, this suggesting that the electric field strength is going to get weaker. So which one of these do you think it's going to be?